I'm going to show you a proof technique known as induction. Like other proof techniques that we've encountered, it works well only for proving certain types of statements. Say that we would like to show a statement that depends on a positive integer n. Here are three examples. The sum of 1 over 1 times 2 plus 1 over 2 times 3 up to 1 over n times n plus 1 is equal to n over n plus 1. And we want to show that this is true for all n greater than or equal to 1. The second one is n squared is less than 2 to the n is less than n factorial for all n greater than 4. The third is that 8 to the n divides 4n factorial for all n greater than or equal to 1. I will show you the idea and the structure behind a proof by induction and then show how it works in these three proofs. The general format for a proof by induction is to first show that the statement is true for some base case. Next, we show that if the statement is true for a given k, then it is true for the next k. We can conclude that since it is true for 1, then it is true for 2. Since it is true for 2, then it is true for 3. Since it is true for 3, then it is true for 4, and so on. We conclude, and we are using the principle of logic here, that the statement must be true for all n greater than or equal to the base case. Let's see how these work for the three statements I gave as examples. I'm going to go through these fast, however I will pause and try and explain some of the finer points about these proofs in general. The three proofs that I show here will be polished. That is, I've gone through the argument completely, and then I figured out what the inductive hypothesis needs to be. This is usually the tricky part about a proof by induction. The precise hypothesis is something you figure out after you've completed the full argument. To show the first statement is true, we start with a base case. N equals 1 is a simple calculation which shows that the left-hand side is equal to the right-hand side. Next, we show that the statement is true for k, then it is true for k plus 1. Usually you show an if-then statement by assuming the hypothesis and proving the conclusion. That is, we assume that the statement is true for some fixed positive integer k. Then, if we replace k with k plus 1 on the left-hand side, we have k plus 1 terms, and the first k of these add up to k over k plus 1. Then using algebra, we reduce this to k plus 1 over k plus 2, and so we have shown that the statement is true for k plus 1. We then conclude that the statement is true for all n greater than or equal to 1. Therefore, by the principle of mathematical induction, the statement is true for all n greater than or equal to 1. Let me make a few remarks here. I am using the variable k because I want to emphasize that k represents a specific instance of the value. It is especially important to make clear that k represents a single fixed value and not all positive integers. This is the biggest mistake I see in induction proofs, that the writer assumes that the statement is true for all positive integers, and then there's nothing left to show, because that is exactly what we're trying to prove. Next proof. The base case isn't starting at k equals 1 here. At n equals 5, n squared is equal to 25, 2 to the n is 32, and n factorial is 120. Since 25 is less than 32 is less than 120, our base case is true. Next, we show if the statement is true for k, then it is true for k plus 1. We assume that it's true for k. I'm going to add the assumption that k is greater than 4, because I found that I needed it in my argument. This is called the inductive hypothesis. Then, check my work carefully as I prove that k plus 1 squared is less than k squared plus 2k plus k is less than k squared plus k squared, which is less than 2 times 2 to the k, which is 2 raised to the k plus 1, while 2 to the k plus 1 is less than 2 times k factorial by the inductive hypothesis, which is less than k plus 1 times k factorial, which is equal to k plus 1 factorial. Therefore, the statement is true for all n greater than or equal to our base case. So by the principle of mathematical induction, n squared is less than 2 to the n is less than n factorial for all n greater than or equal to our base case. Next statement, the base case is 8 divides 24. To prove if the statement is true for k, then it is true for k plus 1. We assume that the statement is true for some positive integer k. That is, 4k factorial is equal to q times 8 to the k for some integer q. Then 4 times k plus 1 factorial can be factored. We replace 4k factorial with q times 8 to the k, factor out of 4, factor out of 2, and then notice that it's an integer times 8 to the k plus 1. So we have that 8 to the k plus 1 divides 4 times k plus 1 factorial. Therefore, the statement is true for all n greater than or equal to 1. So we say, by the principle of mathematical induction, 8 to the n divides 4n factorial, 4n greater than or equal to 1.